Hello everyone. Today I'll be going over some alternate coordinate systems, and I'll discuss Cartesian, polar, spherical, cylindrical, n-dimensional, and different units and scales. And all this is based on Euclidean geometry, which is essentially a straight line is the shortest distance between 2 points, and a few other assumptions. I won't go into too much detail, but this is all on the basis of Euclidean geometry. So first, Cartesian, which is the one most people use. It can also be called rectangular. But before we get to that, let's talk about a simple number line, which is the most basic one-dimensional value. So here, the only thing we can have is a magnitude, and it can be a positive or negative magnitude. And there's no other thing you can do. There's no direction in this case. There's only magnitude. But if we want to introduce another direction, we would simply take this and flip it around, and we would get one direction and another direction. And if we combine these, we would get a plane or a coordinate plane. And here we'll call one direction x and another direction y. And any point on this plane can be labeled a point x, y. And if we wanted a graph, that could be a line of points or an arc of points. We could get y is equal to a function of x, or even x is equal to a function of y. But Cartesian, although it's the one most of us are used to, is not the only way to plot in 2 dimensions. Polar is a different way of graphing. So this point here would be 4, 3 in Cartesian, but polar will use r and theta instead of x and y, where r is the magnitude or the distance of the point from the origin, and theta is the arc length from the positive x-axis to the point. And so r is equal to the square root of x squared plus y squared, and theta is equal to the arctan of y over x, where you would also have to expand this not just from the range of arctan, but from 0 to 360 degrees. And so this point in polar form would be 5, 36.87 degrees, or 5, arctan of 3 over 4. And you could also do it in radians as well. And so generally, if you wanted a graph, you could have r is equal to a function of theta. And what's nice about polar is it's a lot easier to do circular shapes. So let's say we wanted a circle with radius 2, r is equal to 2 would be that circle. So that is r is equal to 2. We could want r is equal to 5, r is equal to anything, would just be a circle of that radius. And so if you want to do math using circles, instead of a x squared plus y squared is equal to the radius squared, you can simply have r is equal to 5, and in polar form that would be enough to fully describe a circle. And there are other shapes you can do. Using trigonometric functions can create interesting shapes. So sine and cosine will make smaller circles. If you increase their frequency, they will make kind of petal designs or flower designs around the origin. If you wanted a straight line, like we can easily do with Cartesian, you would have to use cosecant or secant. So something like this would be 3 cosecant theta, and something like this would be 4 secant theta. And you can add a initial offset to change this angle. So this would be about cosecant theta plus pi over 6 or something like that. And there's a lot more to explore with polar, and it's very useful whenever you're doing radial searches and you don't just want to use 2 orthogonal directions. But polar and Cartesian in 2 dimensions isn't everything. There can also be higher dimensions. So let's look at what higher dimensions would look like. So in 3 dimensions, there's 3 main ways to look at different geometries: Cartesian, spherical, and cylindrical. So Cartesian is just the same way we've seen, with 3 directions. They're all orthogonal, meaning they have a right angle, or they're perpendicular, whatever you want to call it. And the 3 distances combined gives you some point in 3-dimensional space. Spherical will have a radius and then 2 angles. So one angle will get you any point in this plane, and the other angle will rotate the entire plane and give you any point in 3D space. Finally, cylindrical, you have 2 distances and 1 angle. So think of that as like a pipe. So you can have go down the pipe, which is 1 distance. You can go away from the center of the pipe, which is another distance. And then you can turn around in the pipe, which is the angle. So you can radiate away from the center, you can move along the center line, and you can turn normal to the pipe. And so Cartesian is 3 distances, spherical is 1 angle and 1 distance, and cylindrical is 1 angle and 2 distances. And if you notice, all of these add up to 3 for the 3 dimensions, but you always need at least 1 distance to be the magnitude for any geometric system you're using. So that brings us to higher dimensional or n-dimensional. So the most basic, it's obviously 1-dimensional, simply a magnitude. But for any higher dimension, you can either move in an orthogonal direction or a yet unused direction. So this would be a x and y. Or you could rotate the entire plane in a new direction. And so the resultant could be a combination of the original plus rotated in some new plane. And so you can add as many angles and new distances as you want, but you will always need this original magnitude. So Cartesian will be n orthogonal sine distances, so everything can be positive or negative. So it'll be x1, x2, x3, all the way up to x of n. And then angular plus magnitude will be 1 magnitude and n minus 1 orthogonal angles. So there will be an r, and then a whole bunch of thetas until you get to theta of n minus 1. Finally, you can have some mixed system where you have a certain number of distances and a certain number of angles, but they always need to add up to n. So you could have m distances and n minus m angles, and m plus n minus n will get you to n. Finally, let's talk about units and scale. When talking about vectors, which are like arrows that point, so this would be a vector, we can describe them in terms of unit vectors. So while we call this x and y in the coordinate plane, we can also call it I hat and j hat, where I hat is simply 1 unit in this direction, and we call this the I hat direction, and j hat is 1 unit in this direction, and we call that the j hat direction. And so if we want to make some vector, we could describe it in terms of the unit vectors. So this is 3 I hat plus 3 j hat. And we could describe any vector in this space with those rules. So this would be -5 I hat, -2 j hat, or anything else we would want. For 3D space, we would have k hat. I, j, and k are the ones we'll use for 3 dimensions. But there's also another way to orient the scales. We have all been discussing in linear, where this is 1, 2, 3, 4, 5, always adding the same thing. It could be 10, 20, 30, 40, 50, or 2, 4, 6, 8, 10, and so on. But both the axes would be, at the very least, linear scale, even if they're not the same scale. But there's another way to do it, where you could either have both logarithmic or 1 logarithmic. So an example, 1 logarithmic would be, this is 1, and this is 10. This is 2, and this is 100. This is 3. This is 1000. So as you go up this scale, you're multiplying by the same number. As you're going up this scale, you're adding by the same number. And you can also have both logarithmic of different, so you could do, 1, 2, then 4, then 8, then 16, and so on. But generally, having a semi-log scale is nice because you can describe an exponential. So for example, 2 to the x would just be a straight line in a log plot. Because let's say each time, if this is 1, 2, etc., but then this is 2, 4, and in this case this would actually be perfectly straight, but let's say this was 3, 9, 27, where this is a log scale of base 3, there can be any exponential function would be a straight line. And then the higher the base of the exponential, the steeper the slope of the line. And this can be useful for seeing a more general scale of a function. Like it's hard to see on a linear scale, if there's a really wide range of values, it's hard to see small details. But in this case, you could actually see a lot of detail between 0 and 1, because there is 2 to the negative infinity to 2 to the 0. So that can actually tell you a lot of stuff about this. There are also other ways of doing geometric classification. As I said, this is all based in Euclidean geometry, but there's other ways you can do this. So this understanding should get you pretty far in understanding basic geometry and how to represent higher dimensional coordinates and points in different graphing systems. Thank you for watching.